In this video, we are going to do a problem related to mechanical translational system. So, here they are asking what is the transfer function of that mechanical translational system. They given a mechanical translational system. We need to find out the system function or transfer function of that system. So, here determine the transfer function of the system shown below. See here, if you observe the mechanical system given, whether this is translational system or rotational system, means here whatever elements you are observing, those are related to translational system. Why? Because here we can observe spring and mass and dashpot. So, these are the elements in mechanical translational system. We already discussed about mechanical translational system. The basic elements of mechanical translational system are spring, mass and dashpot. Whenever we apply a force on this, then we will get some opposing force from all those elements. So, that force may be applicable on internal elements also. So, here according to that, we are going to move on and we are going to derive the transfer function of this particular system. Coming to here, the output is related to y2 and input is related to f of t. So, in the general manner, the transfer function is nothing but h of s, which is the output transform by input transform, which is equivalent to output transform by input transform. If you consider for this diagram, what we need to derive means we need to derive y2 of s by f of s. Then you are going to get your transfer function of this system. Why? Because for this mechanical translational system, so here the input is f of t and output is in terms of y2 displacement. So, here for this, for any problem related to this model, you need to draw free body diagram. What is the free body diagram of masses? Free body diagram of mass is nothing but which shows you the exact forces acting on a mass element in the diagram. For example, if you want to draw free body diagram for mass m1, I want to give you three important steps. First, you need to ensure whether the system is mechanical translational and mechanical rotational system. So, this is mechanical translational system according to the elements we are having in this diagram. So, now we need to draw the free body diagram and we need to write the force equations. After writing force equations, from that force equations we need to get the transfer function of the system. First, we ensure that this is mechanical translational. So, I am doing second part. So, I am drawing my free body diagrams of mass 1 and mass 2. So, first of all for mass 1 m1, I am going to draw my free body diagram. Free body diagram indicates the total forces acting on that particular mass. So, here this m1, the displacement is y1. So, towards y1 I am considering that y1, and here what are the forces acting means this is the outside force, we need to indicate outwards f of t like this. The remaining forces are due to the elements attached to this mass. What are the elements attached to this mass? So, this is a spring having elasticity coefficient. This is a dashpot attached to this. Due to this also you will get some force, opposing force. So, here we are having friction coefficient B, and here also we are having another spring which is also having elasticity coefficient K2. So, here that all forces are acting on this M1, whatever elements attached to that M1, that we need to indicate here. So, the force due to K1. So, Fk1, another force is due to dashpot Fb, another force due to K2. So, Fk2 and force due to its own. So, that means, so that is Fm1, force due to its own mass. So, force due to mass m1. So, its internal force is having effect and the elements attached to that is also having some force effect. So, here Fk1 force due to this spring, force due to this dashpot, internal force Fm1 and this spring force, whatever the force related to this spring is also applicable here. Now, we will see what about Fm1. We will write each and every one. Fm1 is equivalent to, Fm1 is related to acceleration. So, here that is equivalent to m1 into d square y1 by dt square. How I am writing this equation means we already have an introduction class. What is the force due to mass? So, that is nothing but proportional to acceleration. Acceleration is nothing but d square displacement by dt square. Here displacement is y1. So, proportional to acceleration, proportionality constant must be mass element constant m1. So, like that force due to spring, I already given basic equation in the last class, that is what is the force due to spring, how we can write force due to mass, how we can write force due to dashpot. So, according to that I am writing. After that I am taking the force due to dashpot. So, that is related to velocity. So, that is proportional to velocity. Velocity is nothing but dy1 by dt, and here the proportionality constant should be in terms of dashpot or friction coefficient. So, here Fb is equivalent to b dy1 by dt. Coming to Fk1, so force due to first spring. First spring is attached to some reference and having displacement y1. So spring force is dependent upon the displacement. So, that means, so here this is equivalent to k1 y1. If one end is fixed, this is the formula if one end is fixed. So, everything is the formulas of force when one end is fixed. Why? Because for m1 one end is fixed, for k1 one end is fixed, for b one end is fixed, but for k2 two ends are not fixed. So, this side you are having displacement y1 and this side you are having displacement y2. So, y1 minus y2 we need to consider. So, here if you want to write Fk2, so this is equivalent to k2 into, now we can write y1 minus y2, this will be the resultant displacement. So, this is the free body diagram and the forces, individual forces related to this free body diagram is this. Why I written y1 minus y2 is, this spring is not fixed to a reference, it is having both sides displacement. In this case, in the last class also I told you, whenever you are having like that, you need to consider your force as k2 into that difference displacement you need to consider. So, now after drawing free body diagram and after ensuring all the forces, you need to write the input force is equivalent to all this opposing force. According to Newton's second law, applied force on a body is equivalent to opposing forces. So, now f of t is equivalent to, f of t is equivalent to addition of all these forces. So, that means m1 into d square y1 by dt square plus b into dy1 by dt plus k1 into y1 plus k2 into y1 minus y2. Now, here consider Laplace transform on both sides. What we need to do? Here our intention is to derive the transfer function of the system. At the starting point itself, I told you here the output is y2 and input is f of t. So, if you have y2 of s by f of s in your hand, that is nothing but transfer function. Our aim is to derive y2 of s by f of s. So that's why I am having my time domain. So that's why take Laplace transform on both sides. So by taking Laplace transform on both sides, you are going to get f of s is equivalent to m1 s square y1 of s. You know the Laplace transform equations for d square y by dt square. Differentiation property in Laplace transform, s square into some transform y s square into y of s. So here only one differentiation, s into y of s. So plus b into, when you are having single differentiation, s. For example, d power n by y1 into dt square. So s power n into y1 of s. So how much power you are having there, that much power will come for s. So here b into bs into y1 of s plus k1 into y1 of s plus k2 into y1 of s minus y2 of s. So now here I am taking common of that y1 of s. So y1 of s into m1 s square plus bs plus k1 plus k2. So you can see I taken common of this y1 of s from everything. So minus the remaining term is k2 y2 of s. You just keep aside about this. And coming to second free body diagram, we are having another mass also. We need to consider that effect also. So I am going to take second free body diagram. So of mass m2. So you are having mass m2 here. For this mass m2, the displacement is related to y2. So I am taking in terms of y2. Here there is no any external force up to here. Only at mass m1 we are applying external force, but here I am not having anything. Whatever the forces are there, that means whatever the opposing forces are there, that only I need to consider. So here my opposing forces are related to K2 and internal force. So that means, so here F M2 and F K2, only Fm2 and Fk2, you can see no other forces are going to act on that mass M2. I drawn the free body diagram. So similar to here, I need to ensure the mass elements. So force of that mass M2. So whenever we are writing equation for mass, force of mass, you need to relate for acceleration. Acceleration means d square displacement by dt square. So here displacement is y2. So that's why, so this mass coefficient is m2 and the acceleration is d square y2 by dt square. So now coming to Fk2. Fk2 is equivalent to, so K2 into displacement. So this is related to elasticity coefficient. Force due to elasticity, force due to spring is equivalent to elasticity coefficient into displacement. Here displacement is y2. Now this is the time to write force equation like this. According to Newton's second law, the total force applied at that point is equivalent to opposing force. We are not applying any force on that particular mass. So total force applied is equivalent to 0. We are getting this opposing forces m2 d square y2 by dt square plus k2 y2. Now take Laplace transform on both sides. For this equation also take Laplace transform on both sides. Then what you are going to get? 0 into m2 s square y2 of s plus k2 into y2 of s. So here what you are going to get is, if you take in Laplace transform on both sides, you are going to get m2 s square y2 of s plus k2 into y2 of s. So, now here I am taking common of this y2 of s, y2 of s into m2 s square plus k2 is equivalent to 0. Or you can see we done a small mistake here. Why? Because when you are writing for k2, you need to consider the difference displacement, but we considered I think normal displacement y2. So, here we need to consider y1 also. So, this is a small mistake we done here. So, y2 minus y1 we need to consider. So, here by taking Laplace transform, so you are going to get 0 is equivalent to m2 s square y2 of s plus k2 y2 of s plus minus k2 y1 of s. You can see. So, here also you take common of y2 of s. So, y2 of s into m2 s square plus k2 minus k2 y1 of s. By this I can write y1 of s is equivalent to y2 of s into m2 s square plus k2 divided by k2. So, like this we can write. So, I send this term to this side, y2 of s into m2 s square plus k2 I send this side, and this k2 I send as denominator. So, I am going to get y1 of s. This y1 of s I am going to substitute here. So, if I substituted here, then I am going to get y2 of s into m2 s square plus k2 divided by k2 into I am having m1 s square plus bs plus k1 plus k2, and here minus k2 y2 of s. So, see here, if you want to make, this is k2. So, if you want to make the common denominator, you need to cross multiply. In the next step I am going to do, I am going to cross multiply and take common of y2 of s. So, here itself I am doing. If you want to make this as common denominator, you need to make this as k2 square, and here if you want to take common of y2 of s, so I can take like this. Now, what you want actually, f of s by y2 of s by f of s. You need to send this f of s to this side, this total multiplication factor to this side. Then you are going to get your transfer function of this system. So, finally, output transform is nothing but y2 of s by f of s is equivalent to k2 divided by, so this is m2 s square plus k2 into m1 s square plus bs plus k1 plus k2 minus k2 square. So, this will be your transfer function of the system given. So, here y2 of s is equivalent to k2 by m2 s square plus k2 into m1 s square plus bs plus k1 plus k2 minus k2 square. This will be the transfer function of mechanical translational system given. Only we need to do is, first of all we need to check the number of elements we are having, and we need to draw the free body diagram for masses. We are having 2 masses here, so we will get 2 free body diagrams here. So, how we will draw free body diagram means just by ensuring the forces acting on that body. So, we will write the free body diagram. So, whenever reference is fixed, we will take only one displacement. Whenever reference is not fixed for any element, if reference is not fixed one side, you need to consider the difference displacement. So, here you can see the difference of writing K2 here and here. Here I written y2 minus y1, here I written y1 minus y2. For this body, the displacement is towards y1 to y2. For this body, the displacement is towards y2, y1. So, that is why I written like that. So, you need to write according to the displacement direction. For this mass, when you are writing for this spring, you need to take y2 minus y1. For this mass, to write this spring, you need to write y1 minus y2. So, like this way you need to write the force equations, and you need to finally get the transfer function of the system by taking output transform by input transform.